In the last video, we saw that there are these two ways to view functions, either as an extensional object, where we have pairs, or as an intensional object, where a function f maps some input to an expression. Extensionally, a function can be seen as a kind of distribution. And this distribution can be a multidimensional one, where our inputs and outputs are distributed according to the frequency which they're produced by a natural generative process. Intentionally, we can represent a function as a graph. Say if we had access to its source code, we could construct a graph whose edges represent the data flow through some program. And the idea in machine learning is that even though we may never be able to access the true graph which generated some distribution, if we start with a random graph containing all possible graphs that may have generated this distribution and update the edges in such a way so that the graph which produces the observed distribution is somehow encouraged, and all the other graphs which don't explain the distribution are pruned or thrown away. This process is exactly what Backprop does, and at the end of the day we'll end up with a function f hat which is extensionally indistinguishable from the true data generating process, f. Now I'd like to try to convey an intuition for what this process is doing. And I think a lot of the time when it's presented, there's this picture that's drawn with arrows going in multiple directions. If we think of this graph as a function with two arguments, the inputs and its parameters, theta. So what we're doing when we're evaluating this function is really just matrix multiplication, where say here is our theta and here is our input. And essentially, if we expand this into a scalar expression, we get something like this. And this is just addition and multiplication. There's nothing else to this. We can think of the derivative of this function, and let's say this is a scalar function for simplicity. The derivative is just a function which takes a function over the variable with respect to which we are differentiating and maps this to the sensitivity or the gradient of f at that specific point under evaluation. So this quantity tells us how to update a specific setting of theta in order to reduce the magnitude of f. And this derivative operator really has just a few rules. So if we encounter some variable x, this is just 1. To compute the derivative of the sum of two expressions, then this is just the derivative of the first plus the derivative of the second. Finally, if we have the product of two expressions, then its derivative is just the derivative of the first times the second plus the first times the derivative of the second. And if we look at this scalar expression, then these three rules are the only rules we need to compute its derivative with respect to any of these coefficients, a through j. So to sum this up, there are two ways to think of Backprop. The first is as a stateful process and this process is mutating or updating in place the weights along edges in a graph. And the second perspective is as a stateless process. And this process can be described by a symbolic operator or a higher order function which accepts a function and returns its derivative, or alternatively a function and a variable under differentiation evaluated at a specific setting of that variable and returns the sensitivity of the variable at that point under evaluation.